So we're running through Chapter 10, Lesson 1 today. We're going to look at identifying lines and segments, talking about those parts of circles that we looked at yesterday on our green sheet, looking at special segments within a circle, and looking at tangents and common tangents, and then using the properties of tangents to solve some circle problems. So the first question we see in this chapter is, decide what the names of these segments are. So they list for us, is it a radius, a chord, a diameter, a secant, or a tangent? I've got a couple other symbols in here as well. If we look at AC is here, that would be the radius of the circle. AB goes all the way across, that would be the diameter of the circle. So those are terms we've known for a long time now. DE goes, and that is they've drawn it as a ray, we could write it also as a line. DE goes from point D and extends infinitely and touches the circle in one point. That would be a tangent. AE goes through the circle. We call that the secant. Segment AG would be here. That's the chord of our segment. So a secant creates a chord. If they asked for BE, the book didn't ask this, I'm going to throw this in here. Segment BE is here, we call that the tangent segment. Okay, so it might start at B and go on forever. It might start at E. We could say EB with a ray over it. That would be that would not be a segment. EB would be a tangent segment. Okay, and the important that the tangents are perpendicular to the radius at the point of tangency. That point of tangency would be point B. Things that we've talked about, we talked about yesterday. We talked about this yesterday about if we have a plane, two circles intersecting, possibly in 2 points if they overlap. They could intersect in 1 point if the circles are inside each other, or if they're outside and intersect in 1 point. Those are called tangent circles. They also might have no points of intersection if they are not near each other, or if they're what's called concentric circles. We mentioned that word yesterday. It's also possible you have circles like this inside each other. So it's possible to have 2 points of intersection, 1 point of intersection, no points of intersection, or, as we mentioned yesterday, that strange case where they overlap each other, where there would be infinite points of intersection. So one thing the book focuses on is common tangents. If we have two circles, a line or a segment that's tangent to both of them is called a tangent circle. If the tangents show up inside the circle and intersects the segment that joins the centers of the circles, we call that a common internal tangent. If they don't intersect the segment that joins the centers, we call that an external tangent. So I'm going to start with C. If I draw a common tangent to both of those circles, there's actually one on one side and one on the other one. This one has two common tangents, and they are external tangents. The segment that joins the centers is right here. It's not the line that joins the centers, it's the segment that joins the centers. We call those external tangents because they don't intersect that line. In B, we have two external tangents again. We also have one internal tangent that goes this way. There is a tangent that goes between the two of them that intersects the segment that joins the two centers. We call that an internal tangent. In part A, I don't know why these are not looking like circles, but we have two external tangents. We also, though, have two internal tangents that would go like this. So kind of a weird thing. We can have kind of an X that makes an internal tangent. And again, that is considered an internal tangent because if we connect those two centers, the internal tangents will intersect with that segment. I'm running through this pretty quickly because I know you don't want to listen to me that long, but we talked about this theorem yesterday and I mentioned it earlier. If a line is tangent to a circle, then it is perpendicular to the radius. And they've stated this as an if and only if statement. A line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at the end point of the radius on the circle. And the converse of that would be if the line is perpendicular to if the radius is perpendicular to that line, then it is a tangent. So those are our two ways to talk about tangents, being perpendicular to the radius. We talked about this one also, it's on your green sheet, that those external tangents are congruent to each other. And we kind of proved that in class yesterday using that idea of those are perpendicular. You've got a hypotenuse, because all radii are congruent, you've got a hypotenuse leg congruency, which makes those sides congruent by CPCTC. So then, how do we use those tangents and those ideas of being perpendicular? So this question asks, is ST tangent to P? And we're given lengths here. We're given TP, we're given SP, and we're given ST. Well, this is a let's check Pythag question. Is 12 squared plus 35 squared equal to 37 squared? If it is, then Pythag holds, which means that's a right triangle. If it's not, then it's not a right triangle, and it's not a tangent. And it turns out that is a true statement. 35 squared plus 37 squared, when I take its square root, I do get 37. So 37 squared equals 37 squared. So we would answer that question by saying yes. So showing evidence is checking Pythag. Another question here says, in the diagram, point B is a point of tangency. Find the radius. So for this one, I'm looking at another right triangle, because we know that radius is perpendicular to the tangent. So I can set up a Pythag. My Pythag in this case is going to look like r squared plus 80 squared equals, that entire tangent is 50 plus r. And when I square that, I'm going to write it as 50 plus r squared. And again, you're heading into Algebra 2. Make sure you don't make this mistake in Algebra 2. It's one of our most common mistakes that we see as Algebra 2 teachers. 80 squared equals. Remember, we want to FOIL this out, for lack of a better term. I want to multiply 50 plus r times itself. That gives me 2500 r plus 50r plus 50r, so plus 100r plus r squared. And that 80 squared is 6400. So this looks like a quadratic equation, but what ends up happening is the r squareds are going to cancel out. Sorry, that shouldn't have been 2500r, it should have just been 2500. And as I look through that equation, if I subtract r squared from both sides, this became a lot easier. And I can now solve for my r, subtracting the 2500 from both sides. I get 3900 equals 100r, so r equals 39. Okay, so we can use that idea of the Pythagorean theorem, even if we have to expand a bracket, that's okay. One last question. RS is tangent to circle C at point S, and RT is tangent at T. Find the value of X. Well, that theorem that we had said that if we have a point of tangent C, two tangents from the common point to the same circle, those tangents are congruent to each other, those tangent segments. So that tells us 3x plus 4 equals 28, 3x equals 24, so x should equal 8. Homework paper has some quadrilaterals, so a circle surrounded by quadrilaterals, but they are all tangent to the circles. So we use that idea of this piece has to be equal to this piece is equal to this piece is equal to this piece, and so on, to solve for those missing pieces. All right, that's it. So we're going to work on that worksheet for homework this weekend. Take care, guys. Bye-bye.